Hi, my name is Shifa. I'm from San Jose, California, and my project is measuring the effect of a change in neutrino chemical potential on the primordial value of helium-4 and deuterium. The reason I chose this project is because last year I had done a similar project in the field of astrophysics as well, but I focused more on spectroscopy and capturing deep sky objects. So this year I wanted to focus more on the particle physics aspect. I did so with my partner Jonavi and my mentor, Miss Anne Catherine Burns. Before I begin, I would like to give a brief overview. I will start off by introducing the topic, then talking about the particle physics behind it, the code that we utilized, our results, potential future work, and conclusions. About 13.8 billion years ago, the Big Bang occurred, in which the universe was very hot and dense. This enables an environment for proton to neutron conversions to occur and vice versa, ultimately paving the way for the synthesis of light nuclei in a period of time known as the Big Bang nucleosynthesis. Well, what is the Big Bang nucleosynthesis? Well, the Big Bang nucleosynthesis was the first few minutes after the Big Bang, where there was a rapid production of light elements, specifically lasting from about 1 second to 20 minutes. The two elements that we will study today are helium-4 and deuterium. Helium-4 is an isotope of helium, and deuterium is an isotope of hydrogen. The reason that we focus on these two elements is because they are two of the most abundant elements in the universe after hydrogen 1. Also, their uncertainties are lower, making it a good candidate to study further. After their formation, a small fraction of both these elements were used to fuse together to create even heavier elements. Now, we can observe these light elements in metal poor galaxies, which are galaxies composed of primarily hydrogen and helium. A factor that played a large role during the Big Bang nucleosynthesis was the neutrino chemical potential. Neutrino chemical potential refers to the amount of energy required to add an antineutrino or neutrino to a system. Neutrinos are subatomic particles, and they're neutral. They're also elementary particles, meaning they are not comprised of any smaller substance. Since they are neutral, that means that they do not have a standard electrical charge, but they do interact via the weak force. Their antimatter counterpart are called antineutrinos. Antimatter counterpart refers to a particle that has the exact same mass as another particle, but an opposite charge. So in this case, it has an opposite weak force. As we can see, there is a conversion equation here on the bottom left. This happened between protons and antineutrinos, which then form neutrons and positrons. This equation is telling us that if we decrease the NCP, we are essentially increasing the antineutrinos, which then increases the neutrons, ultimately increasing the neutron to proton ratio and all. This is a particle diagram that my partner and I both made, and it basically models the first second after the Big Bang happened. So after the Big Bang, the protons converted to neutrons and vice versa with the help of neutrinos. And at 1 second, these conversion processes stopped, and a process known as the freeze out. And this is when the universe started to cool down, and so the likelihood of protons and neutrons interacting became less and less. This set up the ratio of the number of neutrons to the number of protons. After 1 second, these neutrons and protons fused together to create even lighter elements. The code that we utilize is called Primordial, and it simulates primordial element production and calculates values of the light element abundances that were formed during the Big Bang nucleosynthesis. For our sake, I won't go too much into this just because there are a lot of parameters, but for our study, we studied the neutrino chemical potential and a little bit of the neutron to proton ratio. For our setup, we started off by running the code without any modification, and this is with the standard theory value of NCP being at 0. Essentially, this was our control that we used to compare our value that we found later on. Then we changed the NCP values for both deuterium and helium-4, and we observed how it affected helium-4 and deuterium abundances. Then we took those values that we got and we plotted them on a graph. These were our theoretical values. Then we graphed the upper and lower bounds, which were our observed values. We acquired these observed values from two sources, the PDG, Particle Data Group, and Empress. The reason we have two sources is because the Empress is a newer source from 2021, but the Particle Data Group is more widely accepted, despite it being older. Then we observed the intersection of these bands and lines. These were our resulting graphs. On the left, we have our helium-4 abundance. On the right, we have our deuterium abundance. For the x-axis, we have neutrino chemical potential. The blue lines are our theoretical values, and the bands are our observed values. As we can see on the left, the PDG matches more closely to our standard theory value of 0 because it hits the graph at a spot where the x-axis is 0. And we can see where the theoretical values intersect with the bands, and this is where the NCP ranges relief tension. Tension occurs when the theory value doesn't match up with the observed value. For our future work, we could potentially study the neutron to proton ratio. NCP directly affects this ratio because it provides the neutrons and it provides the neutrinos and antineutrinos necessary for these conversions to occur. This makes the neutron to proton ratio and the NCP two of the most crucial parameters during the Big Bang nucleosynthesis because they directly affect the light element abundances. In conclusion, our calculated range of NCP values is relatively close to 0, which matches up pretty closely to the standard theory value of 0, except the standard theory value tells us that there is no asymmetry that existed between the antineutrinos and neutrinos, whereas our value is not completely 0, so it gives reason to think that there does exist a neutrino to antineutrino asymmetry. These were our references, and thank you for listening. Any questions?
Thank you, Shifa, for that excellent presentation. And I guess I'll kick things off by asking, so is this a computer program that exists that you learn to use for these numerical predictions?
So our mentor actually made the code, and so she already had it, and she provided us with it. We just had to run it on our terminal, but we did create the code to make the band values that we have, the observed values.
I see. I see. And you mentioned that the standard theory also makes predictions about these values, right? Is that correct?
Yes, yes.
And do we have experimental values from perhaps the microwave background radiation or something that we know for sure?
So for us, since we aren't professional astronomers, we couldn't use spectroscopic methods to actually observe these light element abundances in metal poor galaxies and how the NCP affects it. But we do know that from actual methods, from observing them, we can verify that these values were in fact at 0. And we can see this because of the element abundances that existed in these metal poor galaxies. And these are affected directly by the NCP. So that's how we can kind of get the ranges. But as we proved wrong in our research, the NCP standard value is in fact incorrect. So their observations were not as accurate as it should have been.
Got it. Remarkable. And you mentioned that there could be an imbalance between neutrinos and antineutrinos, right?
Yes.
What would that lead to some kind of significant influence further down the line?
Oh, yes. So for our sake, our research does refine the cosmological models that people can then implement in the real world. But I think I mentioned that if you decrease the NCP, the neutrino chemical potential, it increases the antineutrinos. So this imbalance means that there is a offset in the ratio, meaning there's either more antineutrinos or more neutrinos. We can think about it like a fraction, actually. So if NCP is a number and the fraction has neutrinos on the top and antineutrinos on the bottom. If you have more antineutrinos, you're basically decreasing the NCP values, which affects the element abundances. Whereas if you have more neutrinos, then you're increasing the NCP values, which then affects the element abundances. And based on those element abundances, as I had mentioned earlier, they fuse together to create even heavier elements that now exist in our universe today. So it essentially could alter things like our atmosphere and the composure of our planets.
I see, I see. And so are we able to make observations today that provide us some clues about like what the precise value might have been?
Yes, so since the Big Bang is still a theory, it's not quite an established idea. We could, uh, okay, so using the redshift, we could, on a spectroscopic level, kind of use that range to observe planets or galaxies that are super far away, so meaning they're super red. And based on how old they are, the redder they are, if they're older, they're redder. So then we can use those methods to say, oh, this was probably created more in the early universe because it all started kind of in one central place and then it slowly expanded out. So the places further from us are older. And we can use these methods to then observe the interactions that happen during it or the abundances of these light elements. So that can give us some evidence.
I see. And in terms of the numerical methods you learned and had to use, what was the most challenging part?
So for me, I think since last year was my first year actually doing science fair or the astrophysics field as well, and my mentor was my dad's coworker, so it was like a little bit more casual. And so me stepping into this new kind of workspace and this new math like way of doing things, I think calculating it was a lot more I would say like more brutal in some way because it was just like an exposure to the real world. And I'd say, well, acquiring these values, since I have a little bit of background in Python, but I'm not super familiar with it, I had to learn a lot of new like terminal commands like CD and stuff. And so when I was running these codes, I was kind of having a little bit of trouble, but my mentor was super helpful in supporting me and helping me along the way.
Awesome. And perhaps one final, more personal question. What inspired you to study this problem?
Yeah, so during middle school, I think I had a lot of passions, but I didn't quite know how to turn them into hobbies. It was just kind of an idea in my head. So when I realized that I wanted to do the science fair and my dad's coworker offered to help, he really inspired me because of how passionate he was while he was teaching us. And I realized from the beginning of like the summer from eighth to ninth to the end of ninth grade, I had learned so much. And for me, I really enjoy learning about new topics, especially if they're aside from school, because I feel like the more knowledge, the better and stronger you are as a person. So I was like, I guess that kind of gave me a little boost, and I was super excited. And I was like, I want to do another project in this, and I want to learn something different and new than what I did before because I just want to keep learning about new information. So yeah.
That's wonderful. Well, Shifa, thank you for taking us on this journey from the early universe to what we can observe today in the redshift. And yeah, thank you for the very illuminating and informative presentation.
Yeah, thank you for having me.